you want to ask questions, you should do it in the chat. And then at the end of the talk, Sibylle will try to answer the questions which are written down. Also, we will share notes of the lectures in the chat. So with that said, it's my great pleasure to introduce Sibylle Schroll from the University of Leicester, who will talk about a geometric model for the bounded derived category of a gentle algebra. Okay, please.
Oh, okay. Thank you very much. It's really my pleasure to give these talks. I would like to thank you for inviting me. So the subject of the winter school is representation theory and geometry, and notably, I suppose it's symplectic geometry. And we're interested in Fukaya categories and possibly their in A infinity structure. These lectures on the bounded derived category of gentle algebras and a geometric model for them is sort of an opportunity for representation theorists to understand some Fukaya categories actually in quite some detail. And this is sort of the aim of these three lectures, is that by the third lecture, hopefully everybody can construct their own Fukaya category and see how things behave in that Fukaya category. For this, we need to go through a little bit of combinatorics associated to gentle algebras. Namely, how do these Fukaya categories arise? Well, first of all, it's through the work of Haiden, Katzarkov and Kontsevich, and I will say a little bit about that in the second lecture. But in the first lecture, we're going to simply start with looking at gentle algebras, the definition of gentle algebras. We will see that a gentle algebra encodes a ribbon graph and therefore a surface. And then we will look at the parametrization of indecomposable objects in the bounded derived category in terms of homotopy strings and bands, because this is going to allow us to see these indecomposable objects as curve on the surface in the talk on Wednesday. And so we will see the indecomposables, we will see that intersections correspond to maps. And we will do plenty of examples, compare it with the partially wrapped Fukaya category of a surface with stops, as defined by Haiden, Katzarkov and Kontsevich. And then in the third lecture, we will see how to construct a derived invariant for gentle algebras, which builds on the invariant defined by Avella-Alaminos and Geiss. And for this, we will see that the gentle algebra not only defines the surface, but also a line field on the surface. And this line field has a winding number, or with respect to that line field, every curve has a winding number, and these winding numbers help determine the derived invariant. And if there's any time left, then we'll also talk about derived categories for skew gentle algebras. So skew gentle algebras are a generalization of gentle algebras, and they have a corresponding model in terms of orbifolds. And I believe Claire Amiot will talk about that, where she gives a complete derived invariant for these skew gentle algebras in her joint work with Thomas Brüssel. Okay, so gentle algebras have been around for a long time, so that they were defined in the late 80s by Assem and Skowronski when they were studying iterated tilted algebras of type A. They're defined in their own right in terms of a quiver and relations, and they turn out to be quadratic monomial, which means that they have a quadratic Gröbner basis, which implies directly that they're Koszul algebras. And then it's very easy to see that the Koszul dual is again a gentle algebra. This was first observed by Bessenbrod and Holm, but one can actually directly see it. They are known to be Gorenstein, that was shown by Geiss and Reiten. And again, the Gorenstein dimension can be read off directly off the algebra, because sort of we will see in a moment that they are defined by monomial relations of length 2. And then you count the maximal number of overlapping relations and add 2, and that is your Gorenstein dimension. So gentle algebras are special biserial, which means that they're of tame representation type. That was shown by Wald and Waschbich, but then by Butler and Ringel, when they look at string algebras, they give a parametrization of the indecomposable modules in terms of strings and bands and their combinatorics. So this presentation of indecomposable morphism of indecomposable modules in terms of strings and bands allowed Crowley-Bovey and Krause to describe a basis of the Hom spaces between indecomposable modules. And then in the early 2000s, Schroer and Zimmermann showed that Gender algebras are closed under derived equivalence. So this is an important property, because that means if you have a Gender algebra and you have an algebra that's derived equivalent, then you know that that algebra is up to Morita equivalence against Gender. And I already mentioned that Avella-Alaminos and Geiss have defined a derived invariant that allows to sometimes distinguish Gender algebras, but there are examples of Gender algebras that are not derived equivalent, but that have the same Avella-Alaminos Geiss invariant. So it's not a complete invariant. What is special about Gender algebras is that they're not only of derived, of tame representation type in their module category, but they're also derived tame, and a parameterization of the indecomposable object in the derived category has been given by Beckett and Merklin in terms of so-called homotopy strings and bands. And once we have the description of the indecomposables in terms of strings and bands, Arneson, Laking, and Puxtello have given a basis of the Hom spaces in the derived category. And then in joint work with Tanakji and Puxtello, we have described mapping cones. So we know precisely how some of the triangles look. Right, okay, so this is not an exhaustive list. There's much, much more known about Gender algebras. And maybe this answers the first question, why one should be interested in Gender algebras, or why are they interesting? Well, it's because we really understand them, I would say, completely or almost completely. And so that makes them a really good testing ground for new ideas. If you have an idea and want to see how something works and you don't want to do it for hereditary algebra, then I guess Gender algebra is probably the next best algebra to go to. So since they have been defined, they have been really studied a lot, but then a sort of new interest or renewed interest arose in 2010 when Assembrissel, Charbonneau-Jourdan, and Plamondon showed that the Jacobian algebras of quivers with potential associated to triangulations of surfaces where all the mark points are in the boundary are actually Gender algebras. And really, this paper is the first one that relates Gender algebras with surfaces. I should also mention, I don't forget, there's also work by Labadini at this roughly the same time. Of course, both these works are based on the Fuhrman, Shapiro, and Thurston work. And they give sort of a geometric realization of the Jacobian algebra, of the Gender Jacobian algebras. And notably what is shown, and I've given two examples here because I would like to compare that with the geometric model we get later, or maybe it gives you an opportunity to compare. So how does this work? So here we have a triangulation of a sphere with one boundary, a disk, and we get from this algebra here, it's of course gentle, and then we know that the arcs connecting marked points, so for example this arc or this arc, they are in bijection with the indecomposable module. So these are all arcs excluding these three arcs in the triangulation. And these Jacobian algebras, they can be of finite or infinite global dimension. So here is a Jacobian algebra of infinite global dimension. It arises from this triangulation, where here we have a non-trivial potential. We derive the potential, so we get all these relations of length 2, which I have indicated by dots. So these dots mean that we have relations A, B, B, C, and CA. Relations, so maybe I should say this is I. And then all the arcs in this triangulations correspond to indecomposable objects in the bounded in the module category, to indecomposable modules. Okay, so much for the Jacobian algebras, but then really the interest, I think, for this winter school lies in the following. It's the connection of Gender algebras with homological mirror symmetry. So Haiden, Katzarkov and Kontsevich, they studied what is called the partially wrapped Fukaya category of a surface. So this is an oriented surface with stops in the boundary. There's a certain line field on that surface. And they then show that this algebra here, which a priori is an A infinity algebra, but it is actually formal. So then they show that if you choose, well, they show that if you choose the good generators, and I will say on Wednesday what a set of good generators is. So if you have good generators, then this is formal, and then this algebra is derived equivalent to a graded Gender algebra, which we consider as a differential graded algebra with zero differential. And then we consider the derived category with finite dimensional homology. And the Gender algebras that arise in this context are homologically smooth Gender algebras, but for Gender algebras, homologically smooth is equivalent to finite global dimension. So conversely, if you start out with a graded Gender algebra of finite global dimension, Likely and Polishchuk kind of construct this partially wrapped Fukaya category. One particular instance of this is if the Gender algebra has trivial grading, which we assume here, in which case, of course, we have seen in Keller's lecture that this derived category is simply the bounded derived category of the just Gender algebra without any grading. And by Likely and Polishchuk, this corresponds to some surface Wismart point and a particular line field. So somehow the line field is what gives us the grading of the Gender algebra. And this is what's known as the A side or A model of the homological mirror symmetry. And generally then the idea of mirror symmetry is that there's a mirror on the B side that has similar physical properties. And so the question, of course, what is that mirror? And in the case where we have trivial grading, for certain Gender algebras, Bourbon and Drott have defined some nodal stacky curves. And this was also looked at by Likely and Polishchuk. And they then show that the bounded derived category of coherent sheaves over that nodal stacky curve is derived equivalent to that Gender algebra. So somehow the bounded derived category of a Gender algebra sits in the middle of this mirror symmetry between the A side and the B side. And I have these two arrows here because there's one instance where everybody can understand this. So if the Gender algebra is simply the chronicle quiver, so we have two arrows, and then take the path algebra of that quiver, then on the B side, we all know that this, by Bailenson, he showed that this is the derived category of the chronicle quiver is equivalent to the bounded derived category of coherent sheaves of P1. But somehow there's a sort of on the AR quiver, you kind of cut it up in a different way. On the other side, we can see, hopefully by the end of the lecture, you will also be able to see that here what we get is a cylinder, so an annulus, and this annulus will have two Lagrangians, L1, oops, and L2. And then there will be stops in the boundary. Oops, so here is a stop, and here's a stop. And then somehow there's this reflow, oops, as James, I don't know if James has spoken about that yet, but I think he will later. And there is our Gender algebra. And we will relate this with the geometric model for the bounded derived category here. And then you can really see the correspondence of the geometric model and therefore understand the Fukaya category. Okay, so this is the introduction, but now let's see what Gender algebras are. I hope I have motivated you to really understand them. So the first section is 1.1, Gender algebras and their definition. Okay. Okay, so what is the definition? So a Gender algebra, KQ over I, so it's given by quiver and relations, if when we denote the quiver by a vertex set and an arrow set, Q0 and Q1, we have three conditions. The first one is that for every vertex in the quiver, there exists at most two arrows starting and two arrows ending at V. And then for every arrow in the quiver, there exists at most one arrow B in the quiver, such that AB is a relation. Well, that also works on the other side, so there exists at most one arrow C, such that CA is a relation. There exists at most one arrow D, such that AD is then not a relation, and there exists at most one arrow E, such that EA is not a relation. So a maximal configuration at a vertex is like this. And if we have all four arrows, then we must have two relations. And if this is a relation, necessarily this is going to be a relation. Or the other option is that we have this is a relation, but then we must also have that these two arrows are in a relation. So yeah, so whenever, I think I said that before already, if I write A, B here, and I have a dotted line, that means AB is an I. Okay, but there's a third condition for an algebra to be gentle, namely the ideal I should be generated by the relations in two. So the algebra is generated by these relations, and that's it. And this is very, very restrictive. So first of all, these two conditions here in combination with these mean that if you're at an arrow, then there's at most one arrow continuing to a non-zero element. Okay, so somehow the non-zero elements in your algebra kind of go through the algebra, and there's a unique way in which they go. There's no bifurcation or anything. Okay, so let's do some examples. We've already seen two. So the first one we saw is the A3 algebra. And then we have seen this three cycle with relations, which is an algebra of infinite global dimension. But we can also have parallel arrows, in which case we need two relations like so. We can have loops. So there could be a loop, but then if we want a finite dimensional algebra, we have to have a relation here. So the loop squared is 0. And then the complementing relation would be this relation. And we also allow infinite dimensional algebras here, which we then call locally gentle. So for example, if we have a loop like this, then we could have a relation like relations like this, and that would also be gentle or locally gentle. Okay, so then Pogorjali and Skowronski gave a characterization of gentle algebras. Namely, they show that A is gentle, if and only if the trivial extension of A, which is the semi-direct product of A with its K-linear dual, is special biserial. Okay, so I'm not going to define this trivial extension. but we should know that a trivial extension always is a symmetric algebra. So really what this says is that A is gentle if and only if the trivial extension is a symmetric special biserial algebra. And then Roggenkamp showed for quivers that don't have parallel arrows, and then Antipov showed it in full generality, and I also showed it later again, is that the symmetric special biserial algebra, so if lambda is symmetric special biserial, then this biserial, then this is equivalent to requiring that lambda is a so-called Brouwer graph algebra. So then this means that our algebra A is gentle if and only if the trivial extension is a Brouwer graph algebra. Now, why is that of interest? Well, because a Brouwer graph algebra is defined by its Brouwer graph. So the Brouwer graph algebra is defined by its Brouwer graph. And what is a Brouwer graph? A Brouwer graph is a vertex decorated ribbon graph. So if we know the ribbon graph, then we know the Brouwer graph algebra. And maybe I should also recall what a ribbon graph is. So a ribbon graph is an undirected finite graph with a cyclic ordering at the vertices of the half edges at each vertex of the half edges. And really, what a ribbon graph is a surface, and we'll see that in a moment. But this means if we start with a gentle algebra, then we know that algebra is gentle if and only if the trivial extension is a Brouwer graph algebra. So there must be a ribbon graph somehow. And I suppose a natural question then is, if A is gentle, what is the ribbon graph, or the Brouwer graph is the Brouwer graph of the trivial extension? Okay, so the answer to that is a construction, namely that section 1.2, the ribbon graph of a gentle algebra. Okay, so how is that ribbon graph constructed? Excuse me 1 minute, I seem to have caught a cold. Okay, so in order to construct the ribbon graph for gentle algebra, so from now on, I'll not repeat let A be gentle. I just assume that we're given a gentle algebra A in the form of KQ over I. Okay, so now we first construct the vertex set of that ribbon graph. So for that, let's define some set M, which is given by the maximal path in the bound quiver of the gentle algebra. So these are really the elements of the two-sided socle. So this means P is an M if for any arrow in Q1, we have that PA and AP are in the ideal. And to this set of maximal paths, we add some vertex idempotents, namely the idempotents at the vertices where we have a single arrow sink, a single arrow source, or we have exactly one arrow arriving and one arrow leaving, and the composition should not be 0. And there are no other arrows at V. So if we add this second set here to the maximal path, then as a consequence, we have that every vertex of the Gender algebra Q0 is in exactly 2 elements of M. And what do I mean by is in? Well, either it's one of these, it's one of these vertex idempotents, or a maximal path goes through that vertex, including the start and the end of the maximal path. Okay, but then this really already gives us the ribbon graph. Namely, then the ribbon graph is defined as follows. Define the ribbon graph. Oops, sorry. Gamma A. So it has vertices, the undirected edges, and a cyclic ordering. And the vertices are given by the set M. And then the edges are, of course, pairs of elements of M, because what is an edge? It's uniquely determined by the 2 vertices. And for every vertex in the quiver, vertex V in Q0, we get an edge M and M prime, where M and M prime are the 2 elements in M containing V. So naturally, these edges are in bijection with the vertices of the quiver. And then we note that the elements in M really give you a linear order on the edges attached at a vertex. And the cyclic order is simply the cyclic closure of that linear order. So a cyclic closure of the linear order of the half edges at every vertex. So induced by the elements in M. Okay, and I think the best way to understand this is through examples. But before we do examples, I can tell you this guiding principle, which for people who do a lot of cluster algebras and surface cluster algebras, this will be very familiar, namely the guiding principle is the following. So the path of length 2 really determine the whole of the Gender algebra, and we can cut up the Gender algebra in these paths and then glue it back together. And there are 2 types of path of length 2. Namely, we have either AB and then AB is not a relation, or we have AB and AB is a relation. And in the first case, when it's not a relation, then the ribbon graph locally will consist of a vertex and 3 half edges. And this will correspond to this path here. And if we have a relation, then locally the ribbon graph will be of this form. And the arrows sit on the ribbon graph in this way. And you can technically use this and the gluing to get the whole of the ribbon graph, but if the algebra becomes complicated, it's really easier to use the construction via the maximal path. Okay, so let's do some examples. Because as I said before, a ribbon graph really is a surface, and this is really the way the gender algebras encode the surface. So the first example is the example of simply the A3 quiver with two arrows A and B. Then what are the maximal paths? There's only one maximal path, which is A and B, but then we have all three idempotents in that set M, because 1 is a single arrow source, 3 is a single arrow sink, and then in the middle we have the other condition. Okay, and here it's very easy to check that you have the complete set M, because now every vertex should appear exactly twice in M. And indeed, there's 1, 2, and 3, and 1, 2, 3. So every vertex appears twice. Okay, so now let's do the ribbon graph, and I'll always orient my plane clockwise, and I'll embed the ribbon graph locally in the plane so that the cyclic ordering around the vertices corresponds to the orientation of the plane. And so we have one vertex AB. At AB, I know that they're half edges and that the linear order of these half edges is induced by this element of M. And this is in this way, AB. And then I have the three idempotents, and here they correspond simply to these vertices here. And now the cyclic ordering is, well, here it's trivial at these vertices, but here at the AB, there's exactly one arrow missing to complete that linear order to a cyclic order. And this is precisely the arrow which we would get in the trivial extension if we were to construct a quiver of the trivial extension of A. But what we will do here, we will indicate this arrow as missing, and this will give us later a gluing condition of the vertex onto the boundary of the corresponding surface. So we just record it. Okay, so the second ribbon graph is the one for this gender algebra here, A, B, C. Here our set M is given by A, B, C. Again, we check 1, 2, 2, 3, 3, 1. So we have all the elements. And then when we construct the corresponding ribbon graph, we get that it's simply a triangle. Oops. And our quiver sits in here. So, okay, A, B, C, and the missing bits are here. And lastly, I wanted to give you an algebra where the ribbon graph is not planar, so you don't get the idea that we always get planar graphs. So we have A, B, C, and D, and then our set M is given by AD and BC, and you can check again that we have all the vertices, and if you do the construction, then you have AD here and BC here, and this is the edge corresponding to vertex 1. The edge corresponding to vertex 2 is here, 2 and 3. And you get this ribbon graph, and then the AD sits in here like this. And so we have this one missing, and then B and C sit like this. So this one is missing. Okay, and remember we were asking the question, what is the barograph of the trivial extension of a gender algebra? And this is the answer. So I showed in 2015 that gamma A is the barograph of the trivial extension of A. So you can then directly sort of, you have the equivalent relation of that trivial extension. Okay, but for us, what is more interesting is that a ribbon graph really is a surface, and therefore this ribbon graph is not only a surface, but it gives us a surface dissection. So this is the next paragraph, 1.3 is surface dissection. Of a Gender algebra. Okay, so in general, if we have a ribbon graph gamma, then up to homeomorphism, there exists a unique surface, which is an oriented surface, where the ribbon graph is embedded in such a way that the faces of the ribbon graph correspond exactly to the boundary components of the surface. And for example, you can see that construction in the lecture notes by Laborie. I think they're ETH lecture notes. Maybe you can read that. Okay, so how does this construction of the surface from a ribbon graph work? So you replace the edges of the ribbon graph with oriented strips, and the vertices with oriented disks, and then you glue according to the orientation along the faces. And another way of sort of calling ribbon graphs are also called fat graphs. And so you can sort of imagine that instead of having thin edges, you have bands, and then the bands kind of form the surface. So let's look at our 3 examples. So the first one, remember we had this ribbon graph here. Then if we fatten up the edges, you can already see what we get. We get a surface, that looks like this. The ribbon graph is embedded in that. It has one face, so it's a sphere with one boundary component. Of course, homeomorphically, this is just a disk. And we have this gluing datum. So I'll do it once in detail. Remember, we had the blue cross. And this really tells us that where the cross is where we glue the vertices to the boundary. And for leaves, there's usually no choice. So there's only one boundary we can glue to. So really that in the end, what we get is a disk with a ribbon graph, which is sort of where the vertices are all glued to the boundary. And so what we really have is a surface dissection. Yeah. Okay, and our quiver sits in here like that. Okay, if we do the same thing for example 2, where the ribbon graph was simply this, then we get from this an annulus. And here is a difference, well, already in the first one, but here it's even more noticeable. So if you think back to the Jacobian algebras, we got a disk, but here in this situation, we get an annulus, and this annulus has 3 marked points on one boundary and no marked points on the boundary inside, right? Because the gluing was along here. And then finally, what do we get for this pretzel? So we had this ribbon graph here. There we go. Okay, 1, 2, and 3. Okay, so if you do it, then you get a torus with one boundary component. And I have to say, it's not always obvious when you have the ribbon graph to know exactly what surface it is, but you can use the Euler characteristic of the ribbon graph of gamma is equal to 2 minus 2g, and that gives you the genus, the number of faces of the ribbon graph gives you the number of boundary components, and when you have that data, then you can usually get your surface. So okay, so how does this work here? Oh my goodness, okay, I'm a bit out of time, a bit slower than I thought. Okay, so how does the ribbon graph sit in here? Okay, so we have 1, and then we have the edge 3. So of course we have this identification. And then we have the edge 1, 2. So 2 goes down here and comes back here. And now you can see how the gluing works. So remember we had this one and this one, which would then correspond to this and this. And so if you glue, then you glue to the boundary here and you glue to the boundary here. And if you do this, then I'm not going to draw a new picture. I'm just going to erase it and then do it. So we get one marked point and another marked point, and this was our edge 1. Then we had the edge 3, which went here. And then we have between 1 and 3 is the edge 2, which is here. Okay, so our conclusion really is that if we start with the gender algebra, then we obtain a surface dissection. So we obtain a dissection of a surface. Okay, so this surface dissection is really what gives us a geometric model for the bounded derived category. But in order to describe that geometric model, we also need to consider not only this black ribbon graph, but we're going to define a dual graph of that graph. And so this is the dual graph, gamma A star of gamma A. And usually I will draw the dual graph in red and the original ribbon graph in black. Okay, so how does that work? So we add a red marked point on the boundary between any two black points. If we have an empty boundary component, by that I mean no marked points on the boundary, then I replace it, is replaced by a red puncture. And then the edges of this dual ribbon graph are given by connecting red points with red edges, such that each red edge crosses exactly one black edge, and each black edge is crossed exactly once. Okay, so I think the best way to understand this is by looking at examples. So here we alternate in example 1 on the boundary, the black and the red, and then there's exactly one red edge connecting two red points and crossing this black arc. There's actually one here and one here. So this is the dual graph gamma A star. Okay, in our second example, we have an empty boundary component. So we take it away and replace it by a red puncture. And on the other boundary, we alternate the red and black. And this gives us the dual graph in this case. And finally, here on the torus, I leave it as an exercise to you to fill in the ribbon graph. It's not very difficult, but it's also not very instructive, so I won't do it now. Okay, right. And now that we have the surface, the black graph and the red graph, this completely characterizes gender algebras. So we have the following proposition that we first showed in joint work with Sebastian Oppe and Pierre-Guy Plamondon. And then we did it for finite dimensional gender algebras, and then Palu, Pilot, and Plamondon extended it to locally gender algebras, so to infinite dimensional gender algebras, where instead of red punctures, you also have black punctures. And there's also a related construction by Bauer and Coelho, Simoes, in terms of tilings of surfaces. And what is that? What does this proposition say? It says that there's a bijection between gender algebras up to isomorphism and surface dissections into polygons of the form, well, there are two sets of polygons. Either the polygon has exactly one boundary component or one boundary segment, and then there must be a red mark point on that boundary segment simply by construction, or the polygon has no boundary segment, so it's entirely in the interior, and then it must contain a red puncture. And of course, we have just seen how to go from here to here, but conversely, given such a surface with a dissection of this form, it's very easy to construct a gender algebra. Okay, so that's the first observation. The second observation is that recall that a gender algebra is causal, so it has a causal dual, and the causal dual is again gentle. So the gentle causal dual, which we denote by A shriek, and I'll just briefly recall that that's the X algebra of the trivial module. Okay, so it's potentially infinite dimensional, but it's again gentle, and it has therefore a ribbon graph, and this ribbon graph is exactly that dual ribbon graph, that red one we constructed. Okay, so when we have a surface, and you can see that very easily in this first example, if you look at the red ribbon graph, if you remember before, let me go to our gluing principle here, remember that if we have a relation, then we get this kind of ribbon graph. And if you look here, this is precisely what we get. And of course, we know that the causal dual of A3 is simply A3 with a relation. Okay, and so this gives us the causal dual. Okay, and I wanted to make another remark, and the remark was that the polygons of the form where we have a puncture, so no boundary segments, only appear if the algebra has infinite global dimension. Okay, so now we have all the tools in hand really to describe the geometric model for the derived category of a gender algebra. But in order to really understand how the construction works and why it works, I have to say a little bit about the indecomposable objects in the derived category. So this is then the next step. Indecomposable objects in DBA. So A is, of course, still a gender algebra. Okay, and the first remark is that we construct these indecomposables not in the derived category, but in the corresponding, or in one of the corresponding homotopy category, namely this is the homotopy category of complexes of projective A modules which are bounded on the right and bounded in homology. Okay, and in this category, Beckert and Merklin and also, well, later, so they did it in 2003, and then Boban and Drudge did a different construction, but they also gave, which ended up with the same result. So they give a parametrization of the indecomposable objects, indecomposable objects in this category. And they do it in terms of homotopy strings and bands. And I would like to run you very, very briefly, as quickly as I can, through the construction of these homotopy strings and bands, because when you see it, then you'll really be able to see the indecomposable objects in the derived category as curves on the surface. Okay, so the alphabet, so this is word combinatorics, and the alphabet for our words are the arrows and formal inverses of arrows. So we denote these formal inverses by Q inverse, and basically that means that for any A in Q1, we have an A inverse in that inverse set, such that the start of A is equal to the target of A inverse, and the target of A is the start of A inverse. Okay, and then we can define a homotopy string. So definition. A homotopy string, oops. Sigma is a sequence W1 up to Wm, with each Wi either an arrow or an inverse arrow, such that sigma can also be rewritten as a sequence sigma 1 up to sigma r, where now if I compose sigma I, where sigma I is not the inverse of the next one. So it's not the inverse of sigma I plus 1. So they don't cancel each other, such that the following holds. So sigma I is equal to a subword Wi1 up to Wir with either all Wij arrows, and in that case we would like sigma I not to be 0, or all Wij are inverse arrows, and in this case we want the inverse of sigma I not to be 0. And each sigma I is called a homotopy letter. And we call this homotopy letter direct if it's formed of arrows, and inverse if it's formed of inverse arrows. Okay, so this is one condition. The second condition is if both sigma I and sigma I plus 1 are direct, or respectively inverse homotopy lattice, then we must have that sigma I plus 1 is 0. So that means the last arrow of sigma I and the first arrow of sigma I plus 1 must be a relation. Or in the case where we have inverses, of course, we have sigma I plus 1 inverse, sigma I inverse should be a relation. Okay, so that's the definition of a homotopy string. So it's formed on homotopy lattice, and they need to define some properties. And then we can also define homotopy bands. So a homotopy band is a homotopy string sigma given by sigma 1 to sigma n, such that, well, firstly, it should be cyclic. So the start of sigma 1 is the same as the end of sigma n. And we also don't want them to cancel. So sigma n should not be sigma 1 inverse. We want sigma not to be a proper power of another string for some homotopy string, tau and some m greater than 1. And finally, they should have the same number of direct and inverse letters. And this is simply, this last condition is different from the string case or the module category. And this comes about because now we're dealing with complexes, and complexes sit in different degrees. And somehow when we do our homotopy string, we want to make sure that we end up back in the same degree. So I would like to maybe finish with some examples of homotopy strings and bands. So example. So let's look at two algebras. So the first algebra I would like to look at is this one, A, B, and C. And here we have, for example, the following homotopy strings. We have A, B, then we have C inverse and AB. That's, for example, a homotopy string. But here we also have a homotopy band. For example, this is a homotopy band, and we can sort of see the homotopy letters. So this is the sigma 1, sigma 2, sigma 3, and here we have sigma 1 and sigma 2, and you can see that's the same number of direct and inverse. And so this is a homotopy string. If, however, now we look at a very closely related algebra, 1, 2, 3, where now we introduce a relation here, A, B, and C, then our homotopy strings would look like this. And notably, there's no homotopy band in this algebra. So these are two homotopy strings. Now we have 5 homotopy letters for the first one and 3 for the second, but you can see that we have 2 direct and 1 inverse, so this doesn't qualify as a homotopy band. Okay, so so I guess this is all for today. Next week, we'll see how these homotopy strings and bands define complexes, and then we can move from there to show how they appear as curves on the surface that we constructed today with the ribbon graph. Thank you.
Okay, so let's thank Sibylle for this very nice talk. Yes, so I saw there were 2 questions in the chat. Both of them were answered at some point, but maybe you still want to have have a look at them.
Okay.
So the first one is almost at the top. So after Daniel's.
It's a symmetric special biserial algebra. No, not every symmetric special biserial algebra is the trivial extension of a Gender algebra. So when you have these Brouwer graph algebras, I said that it's a ribbon graph with vertex decoration. And if the vertex decoration is not one everywhere, then that is a symmetric special biserial algebra, which is not a trivial extension of a Gender algebra.
Yes. And then there was a question from Adam Skorisk. I can't pronounce his name. Adam.
What does it mean that sigma inverse is not in I? Okay. I don't know. Is that in the last part where I defined the homotopy strings and bands? Yeah. Okay. So basically the homotopy string, you can see here is a sequence of arrows or sequence of each homotopy letter is a sequence of arrows or inverse arrows. And that sequence of arrows should not be 0 in the algebra. Okay, yeah, right. Okay, so okay, so that's the answer. And when the Gender algebra is Frobenius or symmetric or Calabi-Yau, does its ribbon graph have some special features? Conversely, can we read these properties from its ribbon graph? So I suppose yes. Well, okay. So I think it's Frobenius or symmetric only if your whole ribbon graph or if your surface dissection consists only of polygons that do not have any boundary components. So I suppose your surface would not have a boundary, or all boundary components are empty, and then you replace them with red punctures. So all your polygons have red punctures in them. Does that answer the question? Is there a similar characterization of string algebras in terms of their trivial extensions? I don't know of a similar description or characterization of string algebras in terms of trivial extensions.
So are there any other questions or comments? So that it doesn't seem to be the case. So let's thank Sibylle for this very nice talk.
Thank you.
And then we take a break for 10 minutes until 5:15, when James will give his last lecture.
All right, sounds good.